Okay, so we have been discussing automorphisms of fields, and the recent result we saw is this. If K is a finite extension of some field F, then the group of automorphisms of K relative to F is also finite, and its order is at most the degree of K over F. Now today we are going to see a special field, and we will see automorphisms of that field. Let us recall from ring theory that we have the ring of polynomials over some field F in these n indeterminates, and we already know that this is an integral domain. So being an integral domain, it has its own field of quotients in which it can be embedded, and the field of quotients of it is denoted by this symbol and is called the field of rational functions in these indeterminates. Okay, you understand that although we are calling the elements of this field rational functions, but actually they are not functions. They look like functions, just like polynomials look like functions, but are different from the functions they would define if we use that formula. So just like that, rational functions are simply to be treated as elements of this field. Loosely speaking, the elements here are just quotients of polynomials in n variables. That's what they are. Okay, now this is our field, say, and we want to investigate automorphisms of this field. So what we do, we next consider the symmetric group of degree n. Consider the group Sn, and in Sn let us take a permutation sigma. Now using this sigma, we are going to define a function from this field into itself, and that function also we are going to call sigma, although they are not the same thing, but the author has decided to call that function also sigma. And the definition is this: define this by so this is my input of the function sigma, or rather this function that sigma defines. It is a rational function. This is an element coming from this field, so it's actually a quotient of two multivariate polynomials. The sigma image of this is defined to be this. This is again a rational function in those indeterminates but in place of x1 now we have x1 sigma. 1 sigma is the image of 1 under sigma. Note that since sigma itself is a bijection on this set, sigma is a function like this, no? And sigma actually does nothing but it rearranges this list of natural numbers. So here also we have simply rearranged the suffix values, essentially rearranging these variables, that's it. So that again gives us a rational function, that means again an element in this field. And of course for a given R, this is unique because sigma is well defined. So that is why clearly sigma is, see, this is the problem of using the same notation to denote two different things. Let me to distinguish it from sigma, let me just call it T sigma k. Otherwise it looks very odd. T sigma is well defined. Now our aim is to show that T sigma actually is an automorphism of this field. So let's see how. It's absolutely straightforward, but nevertheless we have to see. So what are the things that we need to show in order to conclude that this is an automorphism? We need to prove that this is a ring homomorphism, and also it needs to be proved onto, and that's it. Because we have already seen that when we are talking about fields, if we have an onto homomorphism, it's automatically one-to-one. So that's all we have to show. So let us first show that this is a ring homomorphism. Let's take two elements in this field and see what T sigma does to their sum, their product. Then it's just a matter of writing, nothing else. On this, if we apply T sigma, so this is basically just this. That means when we apply sigma on this rational function, which is the sum, actually we just simply get this. And that is nothing but the sum of the T sigma values. T sigma. If you want, you can put parentheses. So T sigma preserves addition, and just like that, T sigma will also preserve multiplication. there is a reason that I am calling it T sigma and not sigma like what the author has done in the text. We will see what is the reason for that. Not just simply to distinguish it from our original sigma, there is another reason also. So this is just xn sigma R2 x1 sigma xn sigma. So this is R1, you understand this is going to be R1 T sigma. I am writing briefly, okay, R2 T sigma. And now what about ontoness? Ontoness is actually obvious. Why? Because sigma is onto. So if you have some rational function, alright, that rational function is going to look like this, right? I mean something, and there you just have to replace the suffix values by sigma values of some integers. You see, each suffix value belongs to the set of first n integers, so each one is going to be equal to something sigma, because sigma is onto, and that's why the chosen rational function can be written in this form, and the moment you have it in this form, it then becomes a T sigma. Okay, I wrote that one as T sigma, so I should write this one also as T sigma. So the moment you have that rational function in this form, then that is the T sigma image of some other rational function. That is why T sigma is onto. So instead of writing that much, I am just simply writing also obviously T sigma is onto, but I write within parentheses also the reason, since sigma is onto. Hence, T sigma is an automorphism of our field of rational functions. Alright, now comes the reason for why I am denoting it by T sigma. Let us consider the map which maps sigma onto T sigma. So that means now we are talking about another mapping whose input is this permutation and the output is this automorphism of our field. What kind of map is it? It is of course well defined, but is it something else also? We are going to now show very simply that this is actually a group homomorphism. For sigma and tau in Sn and a rational function in our field, we have this. So what we are now going to do, we will calculate the T sigma tau image of this rational function. where sigma tau is the composition of these two permutations, sigma and tau. So that means we want this R x1, x2 up to xn. We want to calculate this sigma tau. By the definition of our t function, this is R x1 sigma tau and so on xn sigma tau. Now here we have composition of permutations. So by the definition of that, this is just 1 sigma tau x n sigma tau. Again, by our definition of t function, this is x 1 sigma, 2 sigma and so on n sigma t tau. And then of course in the next line we have this, and finally by the definition of composition of functions, because you see these are also after all automorphisms of fields, so there is a composition between them, any two of them. T sigma t tau. Because T sigma tau and T sigma t tau have the same effect on any arbitrary element of our field, so they are equal. Hence, and this equation tells us that this map, although we haven't given it any name, we won't need any name. This map is a homomorphism, group homomorphism. So, the map is a group homomorphism, and that makes the collection of such T sigma a group under composition of automorphisms. That's because we know that the homomorphic image of any group is itself also a group. And so, this is a group under composition of mappings. Mapping, automorphism, same thing. After all, these are mappings. But something else is also true about this function. It's not simply a homomorphism, but it's actually an injective homomorphism. How? Let us take any element in the kernel of this homomorphism. Okay, let sigma be in the kernel of this. You understand from the context, this homomorphism means this one. Homomorphism then T sigma is the identity automorphism on our field. That means T sigma is going to not change any rational function, any element of this. In particular, it will not change the single variables, okay, or single indeterminates. Thus, for any I lying between 1 and n, xi is going to be equal to xi T sigma, because it's identity function. But by the definition of this function, this is what? X I sigma. Now if you go back to the definition of equality in this set, right, and also note one more thing, that this xi sigma in fact are elements not just in this field but in the underlying ring of polynomials, because these are not, I mean, they are quotients. There you can assume that there is 1 or any unit in the denominator, but after all these are elements in this ring. And any two multivariate polynomials are equal if and only if their corresponding coefficients are equal. This is the case no matter the number of variables. It is true in a single variable polynomial ring, it's true in any number of variables, because that's the definition of equality. So xi is equal to xi sigma means that I has to be equal to I sigma, because if I is different from I sigma, then those two polynomials cannot be equal. For example, x1 is not equal to x2. That's because in this polynomial, think of both of them as multivariate polynomials. In this polynomial, the coefficient of x1 is 1, whereas here the coefficient of x1 is 0. So how can they be equal? So that is why if we are getting this, that means I has to be equal to I sigma. But then I is equal to I sigma, and this is true for all I, which means that this permutation does not change any symbol. So sigma is the identity permutation in Sn, that is the identity element in Sn. So sigma is the identity in Sn. But then what have we proved? Sigma we chose to be any element in the kernel of this homomorphism. Sigma has to be identity, which means that the kernel of this homomorphism is trivial, and that just means that our homomorphism is an isomorphism as well. So is an isomorphism but already it maps Sn onto this group. Onto-ness is obvious, and now additionally it's one-to-one as well. Thus, the group Sn is isomorphic to this group. Note carefully that these are actually automorphisms of our field, but this group turns out to be isomorphic to Sn. So now we can say that Sn itself is a group of automorphisms of this field, and it is this that the author means when he writes that Sn is the group of automorphism, is a group of automorphisms of this field. Strictly speaking, that is not true, but because of this isomorphism, because of this identification, that is true. Alright. Now we are going to ask something about this group. That is, what is the fixed field of this group? We now consider the fixed field of Sn. Fixed field of Sn by definition is what? It is the set of those rational functions, each of which is fixed by all the elements of Sn. By all the elements of Sn means by all the T sigmas. By definition, it consists of all the rational functions such that they are fixed under each T sigma, which ultimately means this. One sigma, 2 sigma, and so on, n sigma for all sigma. In Sn. And we know in the background, okay, well, we haven't written sigma here, but we have actually written what it does. Okay, so no need to worry about T sigma. So that is the description, that is the definition of the fixed field of Sn. However, but such rational functions have a name. They are called symmetric rational functions. But these are precisely the symmetric rational functions. The rational functions which are invariant under automorphisms, and that too not just any automorphism, automorphisms derived from permutations of the n symbols. Okay, now being the fixed field, it's a field, okay, and it's a subfield of the field of rational functions. Being the fixed field, it's a subfield of this. called the field of symmetric rational functions, and we are going to denote this field by the letter capital S. Okay, so now S is a subfield of this. We are now going to ask 3 questions about S. The first is this: what is the degree of our field of rational functions over S? Because we are saying that S is a subfield of this, that means this is an extension of S. Then what is this degree? This is one question. The second one is this. What is the second one? Oh, yes. The second one is about the group of automorphisms of this relative to S. What is the group of automorphisms of this relative to S? And there is a third one also. Can we express S as a as an extension of F in a simple manner? Well, actually, what this question asks is precisely this: does there exist a particularly simple set of some special kind of elements in S, so that if you adjoin them to F, you are going to get an extension of F? Can such an extension be equal to S? I forgot the exact language. What has the author written here? What is this? Can we describe S? Can we express S, describe S? They mean the same thing, in terms of some particularly easy extension of F. Yeah, that's what it means. Oh, I was going to write the literal thing, that way we'll eventually find. Can we express S in terms of some simple extension of F? By simple extension, I do not mean that simple extension, that not that technical term, simple extension. And the author says that we are going to answer all these 3 questions simultaneously. And the simple extension means, right now I was saying something, no, that there exists a set of a subset of S consisting of obviously symmetric rational functions, but even more specially some really easy kind of symmetric rational functions which will help us solve, answer all these things. And these things are going to be called elementary symmetric functions. Are they called elementary symmetric polynomials? No, just simply elementary symmetric functions. The elementary symmetric functions in these indeterminates are as follows. And again, let me remind you that by functions we do not really mean functions but elements in this field, and we are going to give them names. A1 is the sum of all the xi's. Which, if we use the summation notation, it just simply becomes this. A2 is the sum of products of xi's taken two at a time, but distinct xi's, no square. Like that, A3 is the sum of products of three xi's taken three at a time, distinct xi's. That means A2 is, it can be written like this: xi xj, where I is less than j, and I and j of course take all the values possible, maintaining this inequality. We are going to give examples, of course. A3, like that, is the sum of this form, where I is less than j, j is less than k, and it goes like this. So as we go down this sequence of functions, eventually we reach an, in which we have all the, it's the product of all the indeterminates, and that's why in this sum there is only one term. So we do not bother writing summation. It is simply just this. Okay, so these are called elementary symmetric functions, but before we say that they are symmetric functions, we need to prove it, right? We need to prove that if we apply those t sigmas for any sigma on any one of these, it does not change, and that is an exercise. That is exercise 7. So we will solve that in the exercise. Right now we take it for granted that these are symmetric rational functions called elementary, okay, because they are particularly easy, which means that all of these AIs are actually elements in capital S. Okay. Now let us see some examples. Suppose n is 2, then we are going to get only A1 and A2, that's it. For n equal to 2, A1 is simply x1 plus x2, and A2 is x1 x2, that's it. We can have only these two. Let us see n equal to 3. In this case, A1 is x1 plus x2 plus x3. Okay, and what about A2? In A2 we will consider xi xj, two indeterminates at a time. That T sigma part is not there in the text. I just did it to make it more clear exactly in what sense the sigmas are automorphisms. The sigmas literally themselves are not automorphisms of our field of rational functions, but they define automorphisms, those T sigmas. But we also see the reason for the author to call them. Do you see why the author chose to write those automorphisms also simply sigma? That's because the group of those automorphisms is isomorphic to Sn. That's why. But anyway, this is A2. So x1, x2. You can see, okay, if you fix I, then choose all the j's that are greater than I. 1, 2, 1, 3, and then you choose 2. So the only symbol greater than 2 is 3 available to us, and then A3. A3 is simply x1, x2, x3. And let us consider the case n equal to 4 also. In this case, we are going to get 4 AIs. A2 will be a little long here. 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. Then A3, taking 3 x's at a time. 1, 2, 3, 2, 3, 4, 1, 3, 4, 1, 2, 4, and finally A4 is just the product of all the indeterminates. Okay, now one can verify, or one actually may know this thing from theory of equations, that x1 and x2 are roots of this polynomial. Do you remember something from your school days? You may have come across this kind of problems where we are given an equation, a polynomial equation, and we have been told that its roots are, say it's a cubic polynomial and its roots are a, b and c. Then a plus b plus c is minus the coefficient of the x term, or I mean x square term. So such things you recall. Okay, I am almost sure that we have all come across such problems. Then we have been asked to show that, say, show that the sum of the roots is this, the product of the roots is this. So from that part we find these things, that x1 and x2 are roots of this polynomial t square minus a1t plus a2. x1, x2, x3 are roots of, I mean you do not have to do anything, you just multiply the product t minus x1 times t minus x2 and you will see that this is the case. Roots of t cube minus a1 t square plus a2 t minus a3, like that, are roots of this minus a1 t cube plus a2 t square minus a3 t plus a4, and so on. Alright, now we are slowly nearing to answering those three questions. Now in that direction, let us first notice this. Since these things, I mean in the general case n, these symmetric elementary symmetric rational functions are all, after all, symmetric rational functions, that is, they are elements in S. The extension obtained by adjoining these elements to F, that is this thing, is a subfield of S. By definition, it's the smallest field containing all these AIs and F. F is of course contained in S and these are also contained in S, so this is a subfield of S. And our claim will now be this. The claim is this. We claim number 1. So the first question was the degree of our field of rational functions over S. We will prove that this degree is n factorial. Okay, this is one of the answers. Number 2, we were also seeking to know the group of automorphisms of this relative to S, that is this. We will prove that actually this is Sn, not isomorphic to Sn, same thing. And the third one is very interesting. The third one is that S turns out to be equal to this extension. Here we are getting the fact that this is a subfield of S, actually it is equal to S itself. So the elementary symmetric rational functions have the power to give us the entire S in the form of this extension. You just need to adjoin all the elementary symmetric functions to the underlying field, and that will actually give you all the symmetric rational functions. Now the proof, of course, I will not do tonight itself. We will see the proof and the subsequent things that come after this in the next field theory video. And tomorrow, of course, we have our, I don't really remember if we have a video or simply exercise problems, but tomorrow we have things. Okay, so that's just it. So see you tomorrow, either in a video upload or in the community section. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.